Hi everyone. In the first part of this video, we'll go through some examples of using the standard error formula, and then we'll look at a situation in which the formula can be shortened so that the calculations are a little bit simpler. Before we go into those examples, we'll review a couple of points about the standard error. The standard error is larger. In other words, the means of the possible samples are more spread out and less accurate overall, when either the sample size is smaller or the population standard deviation is larger, meaning there's more spread or dispersion between the individual people in the population that's being studied. What this is really saying is that when you use a sample mean to estimate a population mean, you're likely to make more error when either you're using a small sample or the population that you're sampling has high dispersion. In those two situations, the mean of your sample is likely to be further away from the mean of the population. The standard error is really just a value that measures how far the sample mean is likely to fall from the population mean. So this is our first example of using the standard error formula. It says example 3 right here, but this is actually example 1 for us in this video. In this example, we have a population of 50 people. The standard deviation of the 50 heights in this population is 4.5. In this example, we're imagining a person who's going around and calculating the mean height of every possible sample of 10 people that could be selected from this population. The person is then plugging all of those sample means into the standard deviation formula to get the standard error. Basically, this person is using the long method of finding the standard error. What we're going to do is we're going to find out what answer this person will get for the standard error after he or she is finished with his or her calculations. But we're not going to use the long method. We're going to use the standard error formula. And to use the standard error formula, we just need 3 pieces of information. We need to know the size of the population standard deviation, and the sample size. So the population size is 50 because the population has 50 people. The population standard deviation is 4.5. That's the standard deviation of all 50 heights in the population. And the sample size is 10 because we're dealing with all possible samples of 10 people. So let's take those 3 numbers and plug them into the standard error formula. So capital N is the population size, little n is the sample size, and sigma is the population standard deviation. Now that we have those 3 numbers, we can plug them into the standard error formula that we learned in the last lecture. So the population standard deviation, which is 4.5, goes right here. The sample size, which is the little n, goes right here. The population size, which is the big N, goes right here. And then the sample size goes right here. And then the population size goes right here. And the -1 is just a part of the formula that's always there. So let's go through all of the steps and get our answer. First, we have to subtract inside of the fraction. 50 minus 10 is 40, and 50 minus 1 is 49. Now we divide inside of the fraction. We divide 40 by 49. 40 divided by 49 is 0.82. Now we find the square root of 0.82. You could find that by just pressing the square root key on your calculator. The square root of 0.82 is 0.91. Now we need to find the square root of 10 right here. The square root of 10 is about 3.16. Now we need to divide the 2 numbers in this fraction. We need to divide 4.5 by 3.16. When you divide 4.5 by 3.16, you get 1.42. Now we just need to multiply. 1.42 times 0.91 is 1.3 if you round the answer. So that's the standard error. That's the answer to the question. Now let's look at another example. This is actually the same situation we looked at last time. A person is going around a population and calculating the mean height of every possible sample of 10 people that could be selected, and then the person is calculating the standard deviation of all of the sample means to get the standard error. Basically, this person is using the long method of finding the standard error. And we want to find out what answer this person is going to get for the standard error, but we're going to use the standard error formula. We're going to use the short way of finding the standard error. Once again, to use the standard error formula, we just need three pieces of information. We need the population size, the population standard deviation, and the sample size. This time, the population size is 100, and the population standard deviation is still 4.5, and the sample size is still 10 because this person is still calculating the means of all possible samples of 10 people. Actually, the only thing that's changed in this example is the population size. The other two numbers are still the same. So we can plug those three numbers into the standard error formula. The population size of 100, the sample size of 10, and the population standard deviation of 4.5. We can plug those three numbers into the formula, and then our answer comes out to 1.3. It pretty much comes out to the same answer that we had last time. I think the answer is a little bit different, but it just became the same after I rounded the answer. Now let's look at one more example. This is actually the same situation again, and the only thing that's changed is that the population size is now 200. The population now has 200 people. And just like before, this person is going around and calculating the mean height of every possible sample of 10 people that could be selected from the population, and the person is calculating the standard deviation of all of the sample means to get the standard error. The person is using the long method of finding the standard error. And just like in the other two examples, we're going to use the standard error formula to find out what this standard error equals. We're going to find out what answer this person will get after he or she is finished with all of the long calculations. So we just need to know our population size, our sample size, and our population standard deviation. Then we plug all three of those into this formula, and then we do the calculations the same way. This time, our answer comes out to 1.4, which is a little bit larger than what we had last time. So that's the answer to the question. The answer is 1.4. Now I want to discuss this last part of the standard error formula. It actually has a name. It's called the finite population correction. And it turns out that this part of the formula actually only has to be used when the population size and the sample size are close to each other. If the population size and sample size are far enough apart, this part of the formula can actually be dropped off, and this over here becomes the entire standard error formula. The general guideline is that if the population is at least 20 times larger than the sample size, then the finite population correction can be left off, and you can just use this as the standard error formula. This is the reason why that part of the formula can be left off when the population size is 20 times larger than the sample size. When the population is 20 times larger than the sample, then the FPC, the finite population correction, comes out to a number really close to 1.